Hi, in this video, I'm going to talk about an article I found and implemented about a year ago. I wanted to give a quick summary of the algorithm and then show a demo of my application. Hierarchical Path-Finding A star, or HPA star, is a hierarchical approach to the standard A star algorithm. The logic behind it can be explained with a simple real-life example. Let's say you live in city A on street B, and you want to move to city X on street Y. You don't consider every single possible road between those two streets and try to find a path from all of them. You don't think at that low level. Instead, you use abstraction and plan based on higher level concepts. First, you decide how to travel from city A to city X. Let's say you have two options, taking a plane or a bus. For this example, let's assume you choose to fly. Now you have an abstract plan. You will go to the airport in city A, take the plane there, and once it lands in city X, you will head from airport to street Y. HPA star works in a very similar way. The first step the algorithm performs is preprocessing. In this stage, the search space, a grid in our example, is divided into higher level clusters. These clusters form an abstract graph where an agent can plan its movement at a higher level. Think of each cluster as a city. Within each one, the agent can plan how to move from city to city. Next, inter and intra-edges are created. Inter-edges are the edges between clusters. To define them, you first choose a grid size, let's say 10 by 10, meaning each cluster covers a 10 by 10 section of the whole grid. Then, when comparing two adjacent clusters, you identify entrances, which are obstacle-free segments between them. If an entrance's width is greater than half the cluster size, in our case 5, two transition points are created, one at each end of the entrance. If the width is smaller or equal, a single transition is placed at the midpoint. These transitions define the inter-edges between clusters. Afterward, intra-edges are created inside each cluster, connecting these entry points. From every entry point to every other entry point inside the same cluster, A star is run once, and the path cost is stored for later use as a pre-computed distance. The paper explains that these pre-computed paths or distances can be cached and reused later when a path request is made. That's exactly what I did in my own implementation, except I stored the actual calculated paths instead of just their heuristic distances and reused them later. This kind of path caching is actually a great optimization strategy in games where multiple path requests come from or end near similar locations. For example, if your NPCs frequently request paths that overlap, caching those computed segments can significantly improve performance. After preprocessing, all these clusters and their connections form a large abstract graph that can be searched efficiently. You can even apply graph reduction algorithms on top of it to make the abstract graph smaller. However, I didn't explore that in my own implementation. Only one problem remains. This graph does not contain the start or goal positions of your specific search yet. It only contains the cluster structure. When an agent requests a path from point S to point G, these 2 points need to be temporarily added to the graph as new nodes. To do this, the algorithm performs a local search between S, the start point, and all entry nodes in its cluster, and between G, the goal point, and all entry nodes in its cluster respectively. Then it connects S and G to their closest entry points in the abstract graph. This connection step can be one of the slower parts of the algorithm. Once S and G are added, a regular A-star search runs on the abstract graph to find which clusters the agent should traverse. Then, each abstract edge between the clusters is replaced with its pre-computed intra-cluster path to reconstruct the full route. Finally, path refinement or path smoothing can be applied. I didn't implement these steps for simplicity, but smoothing can make the resulting path much less jagged. Despite that, the technique still produces paths that are within about 1% of the optimal path length, which is amazing. According to the article, when tested on BioWare's Baldur's Gate maps, HPA star performed up to 10 times faster than a highly optimized A star while maintaining near optimal quality. I can't personally confirm that exact performance gain, since my implementation includes some custom design decisions and there is definitely room for improvement in data structures. But I can say this, the precomputation phase takes a lot of time, and once that's done, it does perform faster than standard A star, even if the path looks a bit rough. First, I would like to demonstrate how inter and intra edges are constructed. To keep it simple, I will use a grid size of 20 by 20, and the HPA cluster size will be 5, meaning we will have 4 clusters, each 5 by 5 in size. Here you can see the world map, our grid, and down below each entrance point is marked with letter N based on the length of consecutive open cells between clusters. Next, you can see the inter-edges being created within each cluster. In this specific example, the top left cluster. Each inter-edge's resulting path is calculated and printed separately. Now, here's a larger working example, a 100 by 100 world grid. The HPA cluster size is set to 10, so we end up with 100 clusters in total. As you can see, each cluster is divided and the inter-edges have been calculated. The inter-edge display is left out here to avoid visual clutter. There's a single path request to a specific coordinate point. The path found by HPA star is shown using X symbols. As mentioned earlier, the path looks a bit jagged. It definitely needs some path smoothing. Yes, that's about it. I believe this is a really clever and powerful algorithm that can be used on large maps to achieve much faster pathfinding. The paper is about 20 years old, and I know there are now even faster approaches, but I wanted to share this technique both as a showcase and as a quick tutorial. Thanks for watching.